Hello and welcome everyone. This is the second podcast for day 4. In this podcast we're going to begin with how electrons are important in chemical reactions, and then we're going to move on to talk about the differences between molecules and compounds, and then the different types of bonds. And then finally we'll close with some chemical reaction definitions that are going to be important as we move forward. Now, this first thing we're going to talk about, if you're looking at your note-taking guide, it actually turns out to be part of Objective 1, but it's a nice introduction to what we're going to talk about here, and that is talking about atom reactivity. And the single most important part of the atom that is important for reacting with other atoms is the electron. Now, in your chemistry class, and perhaps your physics class, you'll talk a lot about electrons and their importance and how they're involved in the structure of the atom. What I want you to know in this class is that if you have two atoms, so you have, we'll just make it atom 1 here and atom 2 here. And the part I circled there is the nucleus of those atoms. And you may have already learned in a chemistry class, or maybe you're learning it right now. But on the outside of these atoms are these electron shells. And depending on the atom that you're looking at, you can have multiple layers of these electrons. It is the electrons in this outer shell, and they exist in pairs, that interact with each other either to share or to donate electrons. So what I want you to know is that two atoms come together and they will form a chemical reaction with each other at the outer electron shell. There are shells, layers of electrons on the inside, and they're not involved in the reaction. It's the electrons in this outer shell that will either donate or share electrons to form molecules or compounds. Now let's talk about molecules and compounds. So first, what is a molecule? A molecule is when two or more atoms join together. Examples of molecules include molecular nitrogen, which we'll abbreviate as N2, molecular oxygen, which we'll abbreviate as O2, molecular hydrogen, which we'll abbreviate as H2. Now what you'll notice is that for these molecules, they're each of the same kind of atom. And this is where molecules and compounds differ. So a compound is a molecule that contains at least two or more different elements. So examples of this would be things like methane, which is C carbon and 4 hydrogens, carbon dioxide, which is 1 carbon and 2 oxygens, or water, which is 2 hydrogens and 1 oxygen. So you can see compounds are also molecules, but they're a special kind of molecule in that the atoms that come together are different. Now, regardless if you're talking about a compound or a molecule, they have to come together by one of various kinds of bonds. And we're going to talk about 4 different bonds: covalent, ionic, hydrogen, and van der Waals. I want to first begin by talking about covalent bonds. I'm going to talk about these first because they are the strongest of the bonds that we're going to talk about. In talking about covalent bonds, let's talk about an example of molecular hydrogen. When 2 hydrogen atoms come together. A key feature of a covalent bond is that they form due to electrons being shared. So let's talk about how this molecular hydrogen forms. You have one atom of hydrogen here and one here. They form this electron shell around them. So this is their outermost electron shell. They each have an electron. In order to complete this outer electron shell, they share these two electrons. I don't want to go into great detail because you'll cover this in a chemistry class, but the reason they can share it is because electrons typically exist in pairs. And so this hydrogen only has one electron and this one only has one electron. And so together, if they share their electrons, they can fill this outer shell, so to speak. This turns out to be a rather strong interaction. Very difficult to disturb this kind of bond. This kind of covalent bond between two hydrogen atoms we call a nonpolar covalent bond. And that is because the electrons are shared equally. So all nonpolar covalent bonds, electrons are shared equally. The other kind of covalent bond is called a polar covalent bond. And that's a little different. So I'm going to erase this and draw an example of a polar covalent bond. So a polar covalent bond is still going to share electrons. But it's not going to share the electrons equally. A good example of this is the compound of water. So we have oxygen here, and then we have hydrogens here. Now the electrons that are shared between these hydrogen and oxygen molecules are not shared equally. So we call this a polar covalent bond. And again, what makes this different than a nonpolar covalent bond is that the electrons are not shared equally between atoms. So the importance of this is that because they're not sharing the electrons equally, this oxygen has a partial negative charge, and the hydrogens will have a partial positive charge, not a fully positive charge, not a fully negative charge, but partial positive and negative charges. We'll come back to this in a moment because this turns out to be really important when we talk about hydrogen bonds. The next kind of bond I want to talk about are ionic bonds. These are fairly strong bonds, but they're not quite as strong as a covalent bond, but they are stronger than a hydrogen or a van der Waals bond. As you recall, covalent bonds are characterized by their ability to share electrons. Ionic bonds are characterized by their ability to transfer, or you might say donate, electrons. When this happens, the result are two atoms of opposite charges. We call these atoms with charges ions. So let's briefly describe ions. Ions can either be a positive ion. When there are positive ions, we call them cations. When they're negative ions, we call them anions. As an example of how one of these ionic bonds work, let's look at a sodium atom and a chloride atom. The sodium atom is going to donate an electron from its outer shell to the chlorine's outer shell. And what that causes is this ionic bond to form. because what the sodium now becomes is positively charged. It just lost an electron, so it lost that negative component of the atom, so now it bears a positive charge. The chlorine atom gained an electron, so now it is negatively charged because now it has an extra electron, which is the negatively charged component of an atom. This positive and this negative now will come together to form an ionic bond in between the two of them. Next, I would like to talk about hydrogen bonds. I remember when I was a student, every time my instructor mentioned the word hydrogen bond, I thought to myself, oh no, not again. Because we talk about hydrogen bonds a lot. We talk about them in chemistry classes, we talk about them in biology classes, but why are they so important? They are a relatively weak bond, certainly weaker than a covalent or an ionic bond. So why are they so important? Well, let's first talk about what a hydrogen bond is. And in doing so, let's draw a water molecule. And remember, this water molecule contains polar covalent bonds with an oxygen atom and 2 hydrogen atoms. And remember, we said these covalent bonds are characterized by the sharing of electrons with their outer shells. But they're polar because they don't share evenly the electrons. And because of that, remember we said this oxygen has a partial negative charge, and these hydrogens have a partial positive charge. Because of these partial charges with the hydrogen and the negative charges of the oxygen, they can form what we call hydrogen bonds. So this compound of water can interact with another compound of water. So you'll have an oxygen here with its partially negative charge, and it will also still have, because it's water still, its hydrogen atoms covalently linked to this oxygen, of course, but because it's polar, we're going to have a partial positive and a partial positive here. And I'm not going to draw it, but now this hydrogen can interact with the partial negative oxygen of the adjacent water molecule. This hydrogen can interact with the partially negative atom of another water molecule. And this one, oxygen, can interact with another hydrogen of a water molecule. Collectively, these hydrogen bonds now will allow water to form in the way that we recognize water. We'll come back to hydrogen bonds periodically throughout the chapters and talk about their importance. Okay, the last kind of interaction I want to talk about are these things called van der Waal interactions. These are the weakest bonds that we're talking about today. I should say individually, because individually they're quite weak. Together, though, they're quite strong. As an example of this, if you've ever seen a smooth surface like a window or a wall, and then happen to see something like a gecko just run straight up it. And you're going to be so impressed right now, I think, with my ability to draw a gecko. There it is. I know. It's awesome. But this gecko is able to run straight up this wall, or the window, or some kind of smooth surface. And it's able to do that because of the hair-like projections on its appendages, on its toes. They are able to interact with this wall, with the elements on the wall. And these interactions are these van der Waal forces. But what are these van der Waal forces? So let's draw an atom. Just a generic one. And we have talked about these electrons on the outer shell of it periodically. And when we draw them, we usually draw them in this kind of nice symmetrical way. And if they were always this way, then we would never see a van der Waal interaction. However, what will happen is that these electrons will sometimes aggregate towards one part of the atom. And when that happens, we can generate partially positive or partially negative charges. And these charges are temporary because these electrons are constantly moving. So for instance, if we had an atom here and it had 8 electrons in the outer shell, and let's say by some chance they all ended up on this side, or maybe not all, but certainly some of them did, or most of them I should say. And over here you had an atom that also had this disproportional distribution of the electrons, but in this case most of them were on this side. What happens now is on this side we have this partial negative charge, and over here we have a partial positive charge. And so we can form this really temporary and weak bond. Now, when you think about all the thousands of appendages, hair-like appendages on this gecko's feet here, and all of the elements along the wall here, these partial positive and negative charges can accumulate, allowing this gecko to firmly attach itself to this vertical incline. Okay, that's all I want to say about van der Waals, and all I want to say right now about bonds in general. Now that we've talked about these different bonds, let's talk about some of the basic nomenclature associated with chemical reactions. First, let's say what a chemical reaction is. We can define this fairly simply by saying a chemical reaction is the process of making and breaking chemical bonds. A chemical reaction will start off with what we call reactants, the starting material of a chemical reaction. And then the chemical reaction occurs, and what we end up with are the products. Something that might not be obvious just by looking at this is that the number of atoms and the kinds of atoms starting in the reactants and ending with the products are the same. So the atoms remain the same. A good example of this is to look at photosynthesis. Photosynthesis is a good example of how we don't change the kinds or the number of atoms. We just change the placement of those atoms. So for instance, photosynthesis starts off with 6 carbon dioxide molecules plus 6 water molecules. Through the process of photosynthesis, the chemical reaction, photosynthesis, we end up with 1 sugar, 1 glucose, plus 6 oxygen. You can count these up, the different carbons and oxygens and hydrogens on both sides, and you'll see that we have the same number. And that's because the number of atoms and the kinds of atoms don't change. They just get rearranged, going from carbon dioxide and water to a sugar and oxygen. That's all I have for this podcast. As you're going through the material, if you have any questions at all, please make sure you come see me. If not, I'll see you in class. Bye.